Right, in this section, we're going to talk about transformations of functions. We're going to talk about symmetry, and we're going to talk about even and odd functions. But we're going to begin by just graphing these functions using just a regular technique, something that is going to help us to describe all of this stuff pretty easily here. So here's a coordinate axis system. And let's do this first one here in white. So some of you might know what this graph looks like, but what we're going to do is we're going to do this using a table of values. All right, so x and f of x, if I can write a little bit neater. All right, I was having a problem changing it over to the eraser, or from the eraser. So if I substitute in a -2, all right, -2 squared is a 4. So my point would be a -2 and a +4. So about there. If I have an x value of a -1, a -1 squared is a 1. So that's going to be there. If I look at a 0, 0 squared is 0, so that'll be the origin. If I have 1, 1 squared is 1, so that would be here. And 2, 2 squared is 4, so that would be here. So my graph is going to be a curve that looks like this. All right. Now, give me a break, guys. I'm not a perfect drawer or artist or anything like that. This is on a coordinate system. So this is a curve, and it hits all of these points that we just talked about. And we got them from using our table of values here. So now let's graph this g of x in green. Okay, x squared plus 3. All right. And we're going to use the same technique here of doing a table of values. Oh, good night. All right. So let's use these same x values here. So if I square a -2 and then add 2 or add 3 to it. So we know that a -2 squared is a 4, and 4 plus a 3 is a 7. So 5, 6, 7. It's going to be there. If I substitute in a -1, -1 squared is 1 plus 3 is a 4. So that's going to be here. If I substitute in a 0, 0 squared is 0, plus 3 is a 3. So that's here. 1. 1 squared is a 1, plus a 3 is a 4. So that's going to be about there. And then 2, 2 squared is a 4, plus a 3 is a 7. So that is going to be up here. So you can see that this graph just slid up 4 units. Okay, that's what the transformation for this one is going to be. All right, let's do this last one, h of x. Let's do this one in green. Okay, so x and h of x. So if I put in a -2, all right, so -2 squared, whoops, my bad. -2 minus 2 squared. So -2 minus 2, that is going to be a -4. And if I square that, I'm going to get a 16. So that's fairly well out of my picture. I'm not going to worry about putting that point on there. So if I do a -1, -1 minus 2 is a -3. And -3 squared is a 9. So that will be up here. All right, 0. 0 minus 2 is a -2, and -2 squared is a 4. So it would be 0, 4, 1, 2, 3, 4, right there. 1 minus 2 squared is a -1, and -1 squared is a 1, so that would be here. Then 2 minus 2 is a 0, and 0 squared is a 0, so that's going to be here. So we get what this side of the graph looks like, okay? But we haven't quite gotten like this other curve or where it turns around. So let's go ahead and put in another point here. And 3 minus 2 squared is 1, and 1 squared is a 1. So that point would be here. So it looks like our graph is going to turn and go this way. All right. So if we're looking at defining these transformations, okay, so if I'm beginning with f of x, the transformation of plus 3 means that this graph is x squared shifted up 3 units. And you can see that from our table of values here and how we got that. Okay. The green one here, h of x, this is x squared, and what did we do? We shifted it right 2 units. Now this one is one that's a little bit interesting because you would look at this -2 and you might think that a -2 means that we're going to be moving things to the left here, but it actually turns out when we substitute the values in, it turns out that it shifts it to the right. Okay, so that's going to be a principle that we're going to talk about. Now, what I'm going to show you next, depending on the textbook that you're working in, these instructions, this table of transformations might look differently to you, okay? But in general, this is what they're going to look like, all right? If you have something outside, not grouped with your x, and it's added in, that's going to shift your graph up or down this many units. So if you have a regular function g of x, a regular function f of x, and then you subtract 3, that means you're going to go down 3 units. If you have a plus 4, that means you're going to go up 4 units. All right. This one is the one kind of like what we're talking about here with the green version here. If you subtract c from the x value, all right, so if it looks something like this, what this means is it's going to move left or right. Okay, now I generally say that if things are grouped with the x, they're going to do the opposite of what you think they're going to do. So if we have an x plus a 4 here, you might think that that's going to shift it to the right 4, but it actually is going to shift it to the left 4, all right, and vice versa. Then we've got a times f of x. This is going to be a vertical stretch or a shrink depending on the value of a. So if a is greater than 1, then it's going to be a stretch. If it is a fraction that's between 0 and 1, or a decimal that's between 0 and 1, that means it's going to be a shrink. And then this one isn't going to be too common, but if you multiply the x by a b, that's going to be a horizontal stretch or a shrink. And again, if things are grouped with the x, it's going to be the opposite of what you think. And then we have reflections. All right, so we're going to take a moment and we're going to move over to Desmos. All right, now what I have here is the function f of x equals x squared. All right, and let me actually move this pane up a little bit here. I don't know how jumpy that was for you. So this is the base function of 1 here, a 0 here, and a 0 here. So really what I've got graphed is y equals f of x. Okay, so that's what this is. This is y equals, x squared. Okay, or I guess you could say f of x equals x squared. Either way, all right? But watch what happens to this function as I start to change this value right here. Okay, I wanted this. All right, sorry about that jump there. I was having to pause to figure out how to get my drawing back. All right, so this is f of x equals x squared. So as I start this animation here, you can see if I'm adding something, it shifts that base graph up, and if I subtract something, it shifts that base graph down, okay? So here I've got -3. You know what, let's go ahead and put this in here. F of x equals x squared. All right, so that's the base graph, right? And so you can see I've got a -3 right here, which takes this graph, it doesn't change its shape, it just slides it. Okay, so we're sliding it down, and then we're sliding it up, and then we're bringing it back to its original position. Okay, so C, if I am adding or subtracting something in here, okay, so this is x plus 4 in here. So notice it is this graph shifted left 4 units. All right, let the animation play out a little bit here. This is x minus 3 squared here. And so that has shifted this base graph to the right 3 units. Okay, so we'll let this play out a little bit further. All right. Now notice when I'm changing C and D, when I'm either adding or subtracting something either inside the parentheses or outside of the parentheses, the shape of the graph is not changing, okay? A is going to change the shape of the graph. So A, if it is, let me just take this slider, if it's bigger than 1, it's stretching it up, okay? If it is 1/2, it is compressing it, or shrinking, I think is the terminology that we're using. Okay. All right. Then you can see that if I have a negative value out here, it takes this graph and it flips it. Okay. So what's that talking about? That's talking about this kind of reflection here. Okay. All right. So, I mean, we can set all of these going at one time, and I mean, we can watch just all sorts of these flips here, okay? It's kind of crazy the way this all looks, okay? But I'll pause all this stuff. And so what is this graph right here? Let's go back to what that is. So what this graph is right here, if I were going to talk about this graph right here. So this is f of x equals 1/2 x plus 2 squared plus 3. Just reading from each of these sliders here. All right. So if you will, if you want to be able to play with this on your own, you can Google Desmos graphing, and you can set up these sliders exactly the way that I've set them up here, and it will give you these options. Okay, so you can set this up, and I'll click on this real quick. So I've set this up to go from -2 to 2, and we're stepping at a 0.5 here, -5 to 5, stepping at 0.1. So if you want to play around with this, then you can do that, okay, to kind of figure out what this is. So this is transformations of functions and how we're going to look at and adjust these things, all right? So now let's talk about symmetry, okay? This graph right here, if you're looking at it, first of all, this graph does not represent a function. It does not represent a function because it does not pass the vertical line test. Okay, so like this vertical line right here does or touches that curve more than one time. This means that it is only a relation, it is not a function. But the way that we can tell that it is reflected across the x-axis algebraically is I can look at, say, this point right here, and this point right here. This is the point -2, 2, and this is the point -2, -2. Notice that the x values stayed the same, but the y values changed only in sign. Okay, that means that when y is replaced with -y, we get this symmetric point here. Okay. All right, so the way that we're going to do this algebraically is we're going to substitute in a -y for every y, and we're going to see what happens with our equation, because we're not always going to have a graph. All right, we're just using this graph as an example. So here, this graph is symmetrical with the y-axis, and you could see that this side over here looks exactly like this side over here. So we could kind of do the same thing. Like let's look at, let's see, what's a good point here? All right, let's use this point down here and this point down here. The x value is a -2. The y value is a -16. Over here for this one, the x value is a 2, and the y value is a -16. So notice the y values don't change, but the x values do change in sign. So this is algebraically, our test is going to be to substitute -x for when we see x and see what we get here. All right. And then origin, again, this one is not a function because it does not pass that vertical line test. But let's try to, well, let's say that this point right here is exactly on it. Okay, so this is the point, it looks like about -3, 2. So if I go to 3 to 3, -2, I should also have a point, okay, because we're replacing both x and y with a -x and a -y. So this is what this kind of looks like graphically. So let's take this function right here and let's test its symmetry. Let's test it for symmetry. All right. So for x-axis symmetry, the test is this. I'm going to replace y with a -y, and I am going to see if I can simplify this equation and get exactly this one. Okay. So there really isn't anything to simplify. I guess the only thing that I could do maybe would be to divide the -1 over. But you can see that no matter how I manipulate this, these two things are not going to be equal to each other. So there is no x-axis symmetry. All right. So now for y-axis symmetry, I'm going to replace x with a -x. All right, so if I square a -x, that gets me x squared. And you can see here that this function or this equation right here is algebraically equivalent to this one. So yes, we do have y-axis symmetry. Okay, so if we look at origin symmetry, I'm going to replace y with a -y and x with a -x. And when I simplify this expression right here, I'm going to get back to the same spot that I was over here with this one. All right, so this one does not have origin symmetry because this equation is not algebraically equivalent to that equation. Or our original one, I guess, is maybe the way that I should say that. All right, let's look at this one. So let's try this again. So x-axis. I'm going to replace y with a -y. All right. I cannot algebraically manipulate this to make this equivalent to this. It just isn't going to happen. So the answer here is no, we do not have x-axis symmetry. Y-axis symmetry. So I'm going to substitute a -x in for the x. All right. If I cube a negative x, all right, if I cube a negative, so a negative times a negative times a negative, that's going to be a negative x cubed. And a negative 4 times a negative x is going to be a plus 4x. All right, is this equivalent to this original function? And the answer here is no. So this, we're not knowing whether or not this is a function or not. And so this equation, if I were to graph it, does not have y-axis symmetry. All right, so origin. So I'm going to replace y with the negative y. I'm going to replace x with the negative x. And I'm going to see what I get here. So I get negative y equals a negative x to the third plus a 4x. All right. So if I divide all of this by a negative 1, let's see what I get here. This will be an x to the third. This will be a minus a 4x. Now notice that this equation is this equation. So yes, we have origin symmetry here. All right. All right. Last one here. All right, so I've got x squared minus y squared equals 9. So let's check first for x-axis symmetry. So I'm going to replace the y with a negative y. If I square this negative y, I get y squared. So this will be x squared minus y squared equals 9. So this equation is equivalent. So if I were to graph it, the answer is yes, we have x-axis symmetry. All right, so y-axis symmetry. I'm going to replace x with the negative x. And if I square a negative x, I get an x squared. And so this simplified equation does look like, and it is algebraically equivalent to this one. So yes, we also have y-axis symmetry. So it's possible for things to have multiple symmetries, okay? Because really, if we look at this one as well, if I subtract x with the negative x and y with the negative y, I'm also going to get an equivalent algebraic equation. So this one really has all three symmetries. All right. So it's possible for things to have multiple symmetries. It's also possible for something to have no symmetry at all. All right. Then we're going to come into this idea of even and odd functions. And this is similar to symmetry, but it's a little bit different because up here we aren't necessarily dealing with functions, but down here with even and odd we are going to be dealing with functions. All right, so if you look at this, what we're going to do in both instances is we are going to evaluate f of negative x. All right, and if it is equal to the original f of x, that means it is even. If it is equal to the opposite of the original f of x, that means that it is odd. So let's take this one for example. So f of negative x here. All right, so negative 5. And then I'm going to substitute in a negative x here. And a negative x here. All right, if I cube a negative x, that's going to get me negative x cubed. So if I multiply that by a negative 5, that is going to get me a 5x cubed. And then here, a negative times a negative is a positive, and 3 times x is 3x. So f of negative x equals 5x cubed minus 3x. Okay? So is this the exact same as this function? And the answer is no. So it is not even. Is it the opposite of the original function? If I multiply this by a -1, do I get this? And the answer is yes. So what that means is that this function is an odd function. All right. Let's look at another example here. All right, I've got f of x equals x to the 4th minus a 6x squared plus an 8. So let us again evaluate f of -x. So I'm going to substitute in a -x. And then I'm going to simplify this. All right. So if I multiply a -x 4 times, okay, if I multiply 4 negative x's, a negative times a negative times a negative times a negative, I'm going to end up getting a positive x to the 4th. If I square a -x, that's going to give me a positive x squared, and if I multiply it by this -6, I get -6x squared. And then there's nothing to do with the plus 8. So is this equal to my original function? And the answer is yes, and that means that this is an even function. Okay. Now our last one here, if we look at it, I'm going to evaluate f of -x. So this will be -x cubed minus 3 times -x squared plus a -x minus a 3. All right, so let's simplify this one here. If I cube a -x, I get a -x cubed. If I square a -x, I get an x squared. So this term will be -3x squared. This will be a minus x, and this will be a minus 3. So right here, this is my f of -x. Is this equal to this original thing? Okay, does it exactly match it? And the answer is no. So it's not even. All right. If I multiply all of this by a -1, is that equal to what I got here? And the answer is no. The signs do not all match. So this one is neither. Okay, so you can have functions that are neither even nor odd. That is a possibility.